Our sun. It's a blazing ball of plasma, the anchor of our solar system, and the source of life as we know it. But the sun is far from a passive provider of light and warmth. It's a dynamic, ever-changing celestial body capable of unleashing powerful bursts of energy. These bursts, known as space weather, can impact our planet, affecting technology and astronaut health. Understanding space weather is crucial for safeguarding our technological way of life. We've all felt the sun's power in warm sunshine or a scorching summer day, but its influence extends far beyond these everyday experiences. Space weather refers to the environmental conditions in space, driven by the sun's activity. It's the constant stream of energy and particles, electrons, protons, and heavier ions from the sun. This stream of charged particles is known as the solar wind. Space has weather too, with radiation, magnetic fields, and charged particles from the sun. Space weather can be disruptive, affecting Earth and our technology. The sun, our nearest star, might seem like a constant presence in the sky, but it's far from calm or predictable. It's a seething, churning ball of plasma, powered by nuclear fusion at its core, where hydrogen atoms are fused into helium, releasing enormous amounts of energy in the process. This energy radiates outward, taking millions of years to travel from the sun's core to its surface, where it's finally released into space as light and heat, sustaining life on Earth and driving the weather patterns we experience. But the sun's energy output is not constant. It goes through cycles of activity, with periods of relative calm interspersed with periods of intense activity, marked by an increase in sunspots, solar flares, and coronal mass ejections. These periods of heightened activity, known as solar maximums, occur roughly every 11 years. During these times, the sun's magnetic field becomes twisted and tangled, leading to the formation of sunspots, which are cooler, darker regions on the sun's surface that are often the precursors to solar flares and coronal mass ejections. Solar flares are sudden, intense bursts of radiation from the sun's surface, like a sudden, brilliant flash of light. Imagine a bomb going off on the sun's surface, releasing a tremendous amount of energy in the form of light, heat, and radiation. These flares are closely associated with sunspots, those cooler, darker regions on the sun's surface where magnetic field lines are twisted and tangled like a knot in a rubber band. When these magnetic fields snap and realign, they release a tremendous amount of energy in the form of a solar flare. These bursts of energy, primarily in the form of X-rays and ultraviolet radiation, travel at the speed of light, reaching Earth in about 8 minutes. While the Earth's atmosphere protects us from the harmful effects of this radiation, it can still have a significant impact on our technological infrastructure. Section 5. Coronal mass ejections, solar storms. If solar flares are the sun's warning shots, then coronal mass ejections, or CMEs, are its heavy artillery. CMEs are massive eruptions of plasma and magnetic field from the sun's corona, the outermost part of its atmosphere. Imagine 1 billion tons of superheated gas, with its embedded magnetic field, being hurled into space at millions of miles per hour. That's a CME. Unlike solar flares, which travel at the speed of light, CMEs are much slower, taking 1 to 3 days to reach Earth. But when they do arrive, they can trigger geomagnetic storms, disrupting our planet's magnetic field and wreaking havoc on our technological systems. These geomagnetic storms can induce electric currents in power grids, potentially causing widespread blackouts, and disrupt radio communications and GPS navigation systems. Section 6. The Earth's magnetic field, our protective shield. Fortunately, Earth has a natural defense system against the sun's fury, its magnetic field. This invisible shield, generated by the Earth's molten iron core, acts like a giant bar magnet, deflecting most of the charged particles and radiation from the sun. It's this magnetic field that creates the beautiful auroras, also known as the northern and southern lights, when charged particles from the sun interact with atoms in the Earth's upper atmosphere, causing them to glow. However, during intense space weather events like a direct hit from a powerful CME, the Earth's magnetic field can be overwhelmed. This can allow charged particles to penetrate deeper into our atmosphere, disrupting satellites, interfering with radio communications, and even posing a radiation hazard to astronauts. On Section 7, Space weather's impact on technology. We live in a technology-dependent world, reliant on satellites for communication, navigation, and Earth observation. Our power grids are the arteries of modern civilization, and our air traffic control systems rely on precise timing from GPS satellites. Space weather, particularly intense events like solar flares and CMEs, can disrupt or even disable these critical systems. When a CME hits Earth's magnetic field, it can induce electric currents in power grids, potentially causing widespread blackouts. High-frequency radio communications, used by airlines, emergency services, and the military, are also vulnerable to disruption from space weather. GPS signals can be degraded or even blocked, affecting navigation systems used by aircraft, ships, and even our smartphones. Section 8. The Carrington Event, a stark reminder. In 1859, the world witnessed the most powerful geomagnetic storm ever recorded, the Carrington Event. Named after the astronomer Richard Carrington, who observed the solar flare that triggered it, this event serves as a stark reminder of the potential power of space weather. Telegraph systems, the internet of their day, went haywire, with some operators reporting electric shocks and fires. The northern lights were visible as far south as Cuba and Hawaii, a testament to the intensity of the geomagnetic storm. If a Carrington-level event were to occur today, the impact on our technology-dependent world would be catastrophic. Power grids could experience widespread blackouts, potentially lasting for weeks or even months. Satellites could be damaged or destroyed, disrupting communications, navigation, and financial transactions. The economic costs would be staggering, potentially reaching trillions of dollars, and the societal disruption would be unprecedented. The Carrington event serves as a stark reminder that space weather is not just a theoretical concern. It's a real and present danger that we must prepare for. Section 9. Recent discoveries in space weather. Space weather research is a rapidly evolving field, with new discoveries constantly reshaping our understanding of the Sun and its influence on Earth. Recent advances in space-based telescopes and computer modeling have allowed scientists to study the Sun in unprecedented detail. One of the most exciting areas of research is the study of the Sun's magnetic field. By using sophisticated computer models, scientists are now able to simulate the Sun's magnetic field and predict the likelihood of solar flares and CMEs with increasing accuracy. Another area of active research is the study of the Sun's atmosphere, particularly the corona. The corona is heated to millions of degrees, much hotter than the Sun's surface, a phenomenon that has puzzled scientists for decades. Recent observations from space-based telescopes have provided new insights into the mechanisms that heat the corona, potentially paving the way for more accurate space weather forecasts. Section 10. Space weather forecasting, a new frontier. Just like we have weather forecasts to warn us of approaching storms on Earth, scientists are working on developing accurate space weather forecasts to give us advance warning of potentially disruptive solar events. By monitoring the Sun with a fleet of space-based telescopes and ground-based observatories, scientists can track sunspots, solar flares, and CMEs as they develop, providing crucial information about their size, trajectory, and potential impact on Earth. This information is then used to generate space weather forecasts, similar to terrestrial weather forecasts, but focused on the Sun and its influence on the space environment around Earth. These forecasts can provide valuable lead time for satellite operators, power grid managers, and other stakeholders to take mitigating actions to protect their systems from the worst effects of space weather. Section 11. Conclusion: Space weather and our future. Space weather is not just an abstract scientific concept. It's a real and present danger that can have a significant impact on our technology-dependent world. From disrupting satellites and power grids to posing a radiation hazard to astronauts, space weather events can have far-reaching consequences. As we become increasingly reliant on technology, our vulnerability to space weather only grows. Understanding the Sun's behavior, monitoring space weather conditions, and developing accurate forecasts are crucial for mitigating the risks and ensuring the resilience of our technological civilization. The future of space exploration, from missions to the Moon and Mars to the potential for deep space travel, depends on our ability to understand and predict space weather. By investing in research, developing new technologies, and raising public awareness, we can meet the challenge of space weather and harness the sun's power for the benefit of humanity.